Okay, we're going to begin with our first web lecture. These are going to be quick lectures on specific topics that we will discuss in class. My primary goal in each of these is for you to understand the significance of terms and how they're going to relate to our discussion in class. So, in our first one, we're simply going to talk about the shape of the Earth. Alright, so, shape of the Earth. Everyone says the shape of the Earth is round. The Earth is round. Well, in reality, that's not quite the way it is. So what we want to do, we're going to have three terms here: a geoid, an ellipsoid, and a sphere or a spheroidal shape. And we're going to ask the question, why does it matter? Why does it matter that we have these three different shapes, and what are we going to use them for? Well, first of all, what we have to say is that in fact the Earth, we conceive of it in the round, if you will, and we can use some measurements that we often use to say that, well, it's equatorial radius, that is a radius from the center of the Earth out to the equator, is just under 4,000 miles. And the equatorial circumference is almost 25,000 miles. Now, notice that in both these cases we said equatorial. The reason for that is that in fact the Earth isn't round. It's not a perfect sphere. What we understand about it is that in fact there's a lot of flattening due to gravity at both poles. In other words, it kind of bulges at the equator, and it's flattened a little bit at the top. Now, we also recognize that the Earth is a very, very complex surface. The terrestrial surface and the ocean's bottom surface are very complex. And in fact, we would not use them for locational purposes because they are simply too complex. So what we do instead is we build different models to do different things. And that's where these three ideas come from. We have the geoidal surface. That's the most complicated. Then we have a reference ellipsoid, which is a simplified mathematical smooth surface. And then we have the most simple idea, which is the sphere. Okay, so we have these three ideas, three different ways of describing the Earth. And we need to understand a little bit about them. Now let's start with the geoid. A geoid, quite simply, is the shape that the Earth would take if it was a fluid, in other words, the surface of the ocean, influenced only by gravity and by the rotation of the Earth. So we've got this idea of where undulations would occur based on gravity. In other words, if there's an excess of mass in an area, geoid is going to be bigger. If there is a deficit, if you will, in mass, it's going to be pushed down. Now, what that represents then is this irregular surface that you see right here. Okay, so again, if we think about it, this is that geoidal surface. Well, if we simplify that and we try to make it into a good approximation that includes the flattening on the top and the bottom and the bulge at the equator, but we want to do it in a simple form that is based essentially on two numbers, the equatorial radius and the polar radius, we get the reference ellipsoid. And if we simplified that down and said, okay, we only want one number, that is a single radius that would describe a sphere, we're going to call that our spherical model. So those are our three differences, and you can see them here. That, in fact, the ellipsoid and the sphere would have a similar vertical radius, but you'll notice, or polar radius, but you'll notice that the equatorial radius would be different between them. And if we compare the geoid to the ellipsoid, we would see that the geoid sticks above it in some places and below it in others. Alright, so now let's take a little bit closer look at this. Again, if we take that geoid and we compare it to the reference ellipsoid, remember our ellipsoid is our smoother model, what we see then is there are some parts of the world where the Earth, that geoidal model, is below. You'll notice those are all the blue areas. And then there are areas where the geoidal model is above, and those are all the red areas. So we'll see that, in fact, the mass of the Earth influences this irregular shape, and we'll see this later on when we talk about vertical measurement. All right, but for right now, the geoid is more complex than the reference ellipsoid. So we can kind of think about the terrestrial surface, and then, if you will, this water approximation, mean sea level, if it was allowed to flow through land. Our ellipsoid, which has, again, a wider or bigger equatorial radius than it does the polar radius, and we call this the semi-major axis, and this the semi-minor axis. And then we have a sphere where the radius in both directions is equal. Now, why does it matter? Here's the important point. If we use a sphere model, each degree of latitude describes an equivalent or equal surface distance or arc distance in units of length. So in other words, the distance between 1 degree of latitude from the equator to 1 degree north would be the same as from 10 degrees to 11 degrees north, or from 89 degrees north to 90 degrees north. Now that's not the case if we use an ellipse. If you think about it, in other words, what we're saying in an ellipse is this distance, 1 degree here at the equator, is going to describe a distance that's very different than 1 degree here. And so that's why what we'll see later on is that we're going to use oftentimes a sphere-based model to describe the Earth in terms of our latitudinal location. Right, so that's the importance. The geoid is a complex surface that describes gravity, and later on, geoids will be used in terms of vertical measurements. Ellipsoids are more precise in terms of their fit to our ideal shape, but they make the calculation of distances in terms of latitude more complicated. And our sphere is kind of the ideal or the easiest one to calculate. So we have these 3 different ways of seeing the Earth, 3 different models. Okay? And again, we will see each one come into play later on. But the main idea is that the sphere produces equal distances for 1 degree of latitude, whereas an ellipse does not. Now, we can see these ellipsoidal distances in terms of something we'll see again later on, which is the differences in the semi-major and semi-minor axis, and this is what we call flattening. And you'll notice it's not a whole lot. 21 kilometers in terms of the distance, the difference in distance between the semi-major axis, that is the equatorial radius, and the polar radius. And depending on which model we use, and they've changed through time, and then as you do your reading you'll see this, there's a slight, and I mean slight, variation in that relationship. You'll notice here between 1972 and 1984, there's only a change of approximately 1 meter. So, again, main idea, ellipses produce variations in the described arc length for a degree of latitude. That is, quite simply, what we're talking about is this distance changes, what 1 degree of latitude describes changes as we move poleward. On an ellipse, it stays constant on a sphere. Okay, that's it for this lecture. We'll pick it up next time.